me and hear me okay. Just waiting for it to pop up on my, aha, it works. So I can also see the chat, which is great. So let me say hi. So yeah, this is partly a trial. I want to test if it works out, and then it's also to ask some questions and have some answers, so we can have a hangout. Hi, Bob. Thanks for joining. Yeah, so if people who are here, if you want to say where you're joining from, let me know what questions you have, then we can hang out and answer some questions, and hopefully the sound is okay. So I've got 2 mics that I tried out, but both of them I don't have the right connections for yet. So that is something that I need to work on. So hopefully you can hear me okay, but otherwise I will work on it for next time. So yeah, let me know if you have any questions. So I can't see the chat there. Let me pull it up here. Make sure the sound is off so that you don't get an echo. Great. Aha. From Los Angeles, welcome. And from London, nice to see you. Thank you for joining. So yeah, what questions do you have? So I've got some already that people sent over from Instagram. So I can answer some of them. I know that not everyone could join live, so hopefully if you sent your question in, then you can join and watch it later if you aren't here live right now. So I'm going to pull those up. Let me get those. So the first question I got is, do I have a PhD? And I think this is actually a great question that maybe I can introduce myself in case you're just passing by and you're wondering why this person is going live on YouTube. So my name is Dr. Clarinellist. Oh, that one said message retracted. Okay. Yeah, my name is Dr. Clarinellist. I am a particle physicist working at CERN. I work for the University of Amsterdam and with NICEF, and specifically I'm working on the ATLAS experiment at CERN. So this is one of the 4 main experiments on the Large Hadron Collider that we have at CERN. And what we're doing is we're taking protons from the LHC and we collide them at almost the speed of light. And those collisions create, it's using Einstein's equation, E equals mc squared. And this means that matter from those protons can be turned into energy and back into new types of matter. Now the matter that's created in these collisions happens all the time in our atmosphere, and they're not brand new particles. But some of them are particles that don't last for very long, and so we want to be able to study them and create them in our collisions and then see what they change into to understand how our universe works. So the question was, do I have a PhD? And I do have a PhD. So I got my PhD from the University of Manchester in the UK. It's also where I did my undergraduate. And my PhD is specifically in particle physics. I was working on upgrading the ATLAS detector. So it has a sort of limited lifetime in the conditions that we run it in with the collisions from the LHC. And it gets radiation damage from all of those particles passing through it. So my job was to design and test new versions of the pixel detector, which is this very first layer that we have in the ATLAS experiment. And we wanted to design versions that were more radiation resistant, that could last longer in those conditions that we have in the Large Hadron Collider. So I completed my PhD, and then afterwards I went on and did a postdoc in France. So I went to work in Orsay, near Paris, at the Linear Accelerator Lab. And after that postdoc, I then went to Göttingen to do another postdoc in Germany. So I spent 2 years there. And after moving, so when I moved to Germany, I started working on top physics, top quark physics. So the top quark is the most massive fundamental particle that we know of in the Standard Model. So out of all of the particles that we have discovered and that we've studied, the top quark is the most massive. And this makes it particularly interesting because we can look at how it interacts with the Higgs boson and other particles, and it can tell us a lot about how our universe works on the very smallest scales. So I started researching that in Göttingen. Technically, I didn't actually start because I did my master's on the top quark at Fermilab in the US. But I was researching it as a post-PhD scientist. And then after Göttingen, I moved to Radboud in Nijmegen in the Netherlands as an Excellence Initiative Fellow. And I spent 3 years working for Radboud, and now I'm an assistant professor at the University of Amsterdam. So that tells you a little bit about my career history. All that time I was working on the ATLAS experiment at CERN, so even though I was working for different labs or universities, I was always researching data or working on the hardware with the ATLAS experiment at CERN. So we have another person joining from the US. Welcome from Raleigh in the US. So welcome. So I got some more questions that I got in through Instagram, but if you have any questions, please do let me know what you want to ask me as a particle physicist. Anything about my research, about working at CERN, any of the videos if you've seen them. Oh, we have a question. Excellent. So I'm going to read it on my tablet because it leaves the phone quite quickly. So the question is from Jeff. It's related to the LHC and dark matter search. Dark matter is a universe galaxy scale force. How does dark matter relate to particle research at the LHC? That is a great question. So we have been looking to see if dark matter is created in our collisions in the Large Hadron Collider. So you're right that, of course, that it's something that we've measured out in the universe on a galactic scale. So dark matter is something that's been measured from the way that galaxies rotate in our universe. So we can measure how fast they're spinning at different parts along from the center to the outside of the galaxies. And we can calculate how fast they should be spinning depending on how much matter we measure that's inside of them, visible matter. And at the edges, they are spinning faster than they should be, depending on how much matter is there that we can measure. There are other signs of dark matter out in our universe. For example, if we look at a large galaxy and we have a bright object behind it, then the light from this object travels to us because the path of the light is bent on its way to us by this very massive galaxy that's in the way. And the light is bent more than we expect from just the stuff, the visible matter again, that we measure out in the universe. So there are lots of signs, there's lots of measurements out in our universe. Hi Julian. that we can see out in the universe that dark matter is there. But we still don't know what it is. Hi. So one of the hypotheses about dark matter is that it could be a new type of particle. We wouldn't necessarily be able to, we wouldn't be able to measure it directly in our detector because it doesn't interact with matter in the way that other visible matter does. But we can see signs that it's there and see how it interacts with other particles if it is a particle through the measurements in our detector. So for example, because it is massive, we know it has mass because of the way that things are bent in our universe, then it could interact with the Higgs boson, or it could affect the way that the Higgs boson interacts with particles that we know about. So that's one reason that we really want to study the top quark that I was talking about and how it interacts with the Higgs boson. Hi, welcome to the live. So we want to see how the top quark and the Higgs boson interact with each other, for example, because if the interaction is not the same as is predicted in the standard model, if there's something else going on there, it could give hints that there are other particles interacting with the Higgs field that aren't predicted in the standard model, and the dark matter isn't in the standard model. So this is one way that we're looking for it in our data. We also look for it by looking for bumps in different, we call them channels. So we will measure different types of particles being measured in our detector and plot that on a graph. And then we look for new bumps that show that there's another type of particle that changes into those ones in our plots. So this is, this is how we look for dark matter. We're looking for things that are missing, or we're looking for things that are there that we don't expect. And we very precisely measure all of the particles that we do know about from the standard model and see if there's anything unexpected happening. So hopefully that answers your question. Let me know if you have any follow-up questions. So I'm also going to be drinking my tea because it is in the evening. This is a decaf tea though, because it's quite late here. And as I said, so if you, oh, brilliant. Glad that that answered that for you. So if you saw my Twitter post, or I posted also on YouTube, mostly I'm trying to test if this works. I'm trying to see if people are interested in having these question and answer sessions. I want them to be quite casual, quite friendly, where we can discuss different particle physics and things that are happening at CERN during the live stream. I'm also going to be working on more longer videos, so if you're interested in those, this is my little plug. Please go and subscribe to the channel because there will be longer videos coming out soon, and there will also be a lot more shorts because that's mostly what I work on. So I create short videos to explain particle physics and other physics research. So there'll be more than Julian. So Julian says that he should have prepared some questions, but there'll be more lives. There'll be more chances to ask questions. So is it Oswago? I hope I've said your name correctly. Asks, for those interested in the Atlas experiment or doing internships at CERN, can you provide more information? So absolutely. So it really depends what stage you're at in your career. If you are an undergraduate in science, technology, engineering or maths, then we have the summer student program at CERN. It's mostly aimed at people who are around their sort of third or fourth year. And it's a 9 to 12 week program where you can spend time at CERN doing lectures, doing a project with a supervisor, and just getting really immersed in the life at CERN, meeting other people there, discussing physics, discussing everything that's happening at CERN. And so unfortunately the application for that has just closed, but there'll be another opportunity that opens next January is usually the best time to be applying. We also have technical studentships, so you can spend up to a year at CERN. And that's much more for the technical work, for the hands-on work, either in the experiments or as part of the accelerator teams. And I actually don't know the deadlines for those. I'll check and I'll put it in the comments for this video if you're watching later. But you can definitely, for all of the opportunities, you can go to careers.cern. And we have lots of opportunities to apply to be at CERN. Aha! So Bob has put the link for the summer student program in the chat. And then there's also the technical student program. So hopefully I say your name correctly. Is it Ritanshu? Asks, can you tell me about the nature of potential interaction between quark and the gluon inside the hadron? So yeah, inside the hadron, we have 3 main quarks. So these are mostly up and down quarks, and they are held together. Brilliant, Bob is putting all the details in the chat. So the deadline for the last technicals, for the current technical studentship is March 27th. So that's loads of time, it's about a month to get an application in. So you should absolutely apply for that if it applies to your current situation. So yeah, so for the hadrons, we have up quarks and down quarks are bound together. So the gluon is really the force that holds these particles together. But actually, for example, protons are a bit messier than this. So they also have what we call valence quarks, which are other, hold on one second. Hold on, I just had a message. Yeah, sorry. So we have quarks inside the proton, which are held together by gluons. And then we have these other quarks that pop into existence in pairs, so quark-antiquark pairs. And this creates quite a messy proton structure, so that when we collide them together in the center of our experiments, in the center of ATLAS or CMS or LHCb or ALICE, we don't know exactly which particle, which one of the quarks or which one of the gluons is doing the collision, which makes hadron colliders, which is the H in the LHC, quite messy, complicated equipment for doing research with. But the reason that we use protons rather than, for example, an electron, which is a lighter particle and is fundamental, is elementary, is because protons are more massive, which means we can accelerate them in the same size of accelerator to higher energies. So we smash these bundles of quarks and gluons together, and it allows us to search a whole a huge energy range, to be able to look at different types of collisions and different things that happen inside those collisions. So Julian asked a question, which is, can you name the top 5 things that you're working on at the moment, or that keep you and your colleagues at CERN awake at night, so the audience can decide which one to ask about? Great question. So dark matter is a big question. So we know that it exists in our universe, but we don't know what it is. If it's a particle, that would be great, because hopefully we can try to discover it in our collisions, but we're also setting limits if it's not one of those types of particles. So even if we don't find it, it would be not great, but it's still useful scientific information. We also want to know why matter and antimatter, which should have been formed equally at the beginning of our universe, why there's more matter left over than antimatter. So apart from the difference in electric charge, they should be essentially the same. So it's really interesting when people talk about antimatter as though it is this weird, strange matter. But there could have been a universe where there was more antimatter left over than matter. And as far as we would know, it wouldn't really seem that different. We would then be antimatter beings with anti-protons making anti-atoms, but we wouldn't call it anti because that would just be ourselves. But there must be some slight difference in the interaction and the way that they change into each other that left us with more matter than antimatter. So this is one of the big questions that we have as well in particle physics. What other questions? That we also want to understand the nature of gravity, but that is, it's a bit more challenging with the Large Hadron Collider. So Joseph says, we need CERN to make antimatter so we can travel to another galaxy. We can make antimatter. We have a whole antimatter factory, which is great, but we don't make very much of it at all. It's like nanograms is maybe the most we've made. Mostly we make a few particles. Well, we make lots of particles at a time, but in terms of studying it, we end up with just a few. So really the challenge is the storage of antimatter, because we can't get it to hang around for very long, because as soon as antimatter touches the wall of a container, then it annihilates and we're left with energy, but not with our antimatter anymore. So storage is the big challenge, because also if you want to put it in a spaceship, you've got to have a storage container that can keep that antimatter from not touching the sides of the wall while your spaceship is traveling and potentially accelerating very quickly. So that's a really big technical challenge, but yeah, it's very interesting, and I'm sure people working on that, yeah, I'm sure, well, there are people working on that, but I'm sure that in the future we'll have some updates on that, but not right now, unfortunately. We can barely get it across the road, never mind, and that's individual atoms. Great, so Advait, I think is how you say your name. Are physicists expecting any new physics at the high luminosity run in 2029, or is it just to push the accelerator to its limit? Yeah, so I just saw Julian's comment. So I've got two more for you. I will get them soon. So yeah, the question was, are we expecting any new physics with the high luminosity LHC? So for those who aren't aware, the high luminosity LHC is the upgrade of the accelerator, and luminosity for us means the amount of data that we are producing. So the high luminosity LHC will take the bunches of protons that we have and make them even more closely packed together, so that when we collide them, there are more protons colliding each time those bunches in the LHC are crossing over each other. So at the moment we have a maximum of 60 happening, 60 collisions happening every time they cross, and this is partly tuned by the accelerator physicists. But when we make those protons even more closely packed together, we're hoping to get up to about 200 collisions happening at once. And that is a lot for our detectors to deal with. So first of all, it's a huge challenge for us as well. So the accelerator teams are working hard to prepare the machine so that it can go to this high luminosity. But for the detector side, it's going to be a huge challenge to be able to measure that data. If you have 200 collisions happening at once in the center of our detector, and from those collisions, a new particle like a Higgs boson or something else is created, maybe even some dark matter, and then they change into other types of particles which come off in a sort of firework shape from the center of the collision. And these have to then be measured very precisely in the different layers of our detector. Then we have to reconstruct those particles that we have measured, track them back, and say, okay, these ones came from this collision 1, these ones came from this collision 2, ... these ones came from this collision 200. And that is a very challenging technological step that we have to do in our detectors, but we are upgrading our detector to be able to do this, and then we will have a significantly larger data set to study. So at the moment we've created about 10% of the data that the LHC is expected to produce. So we've still got 90% of the data left to go. The actual energy of the collisions is not expected to go up very much if we decide to increase it at all. So at the moment we're at 13.6 TeV for the collisions in the Large Hadron Collider, and the LHC is designed for 14 TeV. So that's sort of the maximum we were expecting to be able to go to with the Large Hadron Collider. So even if we do make that step towards 14 TeV, it's not a huge energy jump. It would still be a huge achievement to be able to get the LHC to that energy, center of mass collision energy, but we're not sure. So looking at that energy range, it's more about precision of the data. So once we get that significantly higher data set, then what we can do, because when we collect the collisions in the Large Hadron Collider, we then sort of isolate the data for the bit that we're interested in. So in the ATLAS experiment, for example, I'm interested in top quarks, and I have to make selections on my data to sort of chop it up and take this little bit and then look for the things that I'm interested in. So the big achievement with having the high luminosity LHC is having a huge amount of data. So then even when I've done my chopping up, I've got a huge amount of data and we'll be able to look for much rarer events in the LHC. We'll be able to make even more precise measurements of the particles that we already know about. And so perhaps if there are new particles coming up in our collisions, we might not have seen them yet because there's so much background, there's so much other stuff going on in those collisions. But with the higher amounts of data, then we can isolate it better and hopefully find either those new particles, the new forces, or just better understand the particles we do know about, which might give hints about other things that are going on in our universe. So I can't make any promises. That's why I'm being the way that I am, because when we started with the Large Hadron Collider, we knew that the Higgs boson would either be discovered or it would be completely ruled out, because we'd looked basically everywhere else except for much, much higher energies that theory had said, no, it's not up there. It's in this set of data, this energy range, and either the Large Hadron Collider would find the Higgs boson or it would rule it out completely. Now we know that there are questions we have about the universe, but we don't have this specific roadmap. So we have to do really precise measurements and we have to look for those bumps to see if there's a new particle or anything else happening in our data. So that's hopefully answered your question about the high luminosity LHC. So Eric asks, what are currently the most interesting measurements to learn more about the standard model, i.e. not new physics searches? So yeah, one of the big questions right now, and so this also hopefully then answers one of Julian's questions, is that we had a recent update from a different experiment from Fermilab in the US, which actually stopped running in 2011. And they spent an extra 10 years analyzing their data. So even once you've collected all of the data with new analysis techniques and new ways of processing the data, it's possible to still analyze it and search for information about how our universe works. So this was the CDF experiment in the US, and they released a new measurement of the W boson mass. And W boson is one of the forces that we have in the standard model, or the force bosons in the standard model. And they measured its mass, and it was about 1% different to what the standard model predicted. And what was even more interesting was that it was different to what other experiments had measured it to be. So the D0 experiment, which was also in Fermilab, and CMS and Atlas, which are on the LHC at CERN, those three experiments don't agree with this new CDF measurement. And if the W boson mass is that different to the standard model, then that tells us that maybe there is something else going on. But one experiment measuring this is not enough. So what we're going to be seeing coming up in the future are new measurements from Atlas and CMS at least, that are going to be measuring the W boson mass and comparing it with the CDF result and seeing how well they agree with it now that we've collected even more data. One of the challenges for the W boson mass measurement is that because we're colliding protons, like I was saying, they're very messy, so it's more precise to measure with electrons, but we can't do that with the LHC because we don't get to the energy ranges that we want to get to. So the W boson mass is one that's going to be interesting to watch in the coming years. But it's a very challenging analysis, and therefore it takes a long time to do, and you have to really understand your detector very, very precisely. So, I'm going to answer another one quickly from Instagram because people sent them in and I don't want to not answer any of them. So somebody asked about tips for getting into the summer student program. So we did already talk about that. My biggest advice if you're going to be applying for the summer student program or for any of the programs that we have at CERN is really to make sure you do your research. So you should have some understanding of whether you want to work in one of the detector collaborations. Do you want to be an accelerator physicist? Do you want to be an engineer? Some of it also depends on your background, but research the different groups that we have here at CERN. Somebody says, I don't know how I got here, but very interesting. Well, you're welcome. So research the different groups that we have at CERN, the different areas, and then kind of tailor your application to them. I wouldn't make it so specific that you're really just applying for one, say, analysis within a collaboration, but show that you have done your research, that you know what you want to be doing when you get to CERN, because that will really help you stand out when people are looking through the applications. So Julian says he's a pilot. Can I work at CERN? We do have an airport nearby. So Geneva Airport is very close. But you're not too old. So when I was a PhD student, there was somebody who was joining the same year as us to do his PhD, and he just retired from a big tech company. And he decided that just before he really settled into his retirement, he wanted to do a PhD and work at CERN for 4 years. So that's what he did, and I don't think you're ever too old to learn and to get involved. So, so I was answering, so for the summer student program, really showing that you've done your research and you know what's going on at CERN is a really good way to stand out. And for the summer student program specifically, you need to have good references. So make sure you ask people well in advance. You can give them some tips, some extra things that you've been working on that they could add in their reference letters. So, so I'm reading the comments as I'm going along. So make sure that that the people who are writing the reference letters for you, because for the summer student program there isn't an interview, are putting your best side forward. So that's my best advice for the summer student program. Let's have a look on Instagram. Somebody asked what the food's like at CERN. It's pretty good. They do cooked lunches. We have a canteen, which is pretty good. Lots of options. I tend to go for pizza and pasta quite a lot, but there's other cooked options and sometimes special. So we have a sushi on some days. So yeah, the food's pretty good. And hanging out afterwards, we have drinks also are available in the evening. And so it's very sociable. It's a great place to meet people going for coffee in the restaurants at CERN. So the social aspect of CERN and discussing with people. I love walking around the restaurant and you can just, you can hear all these different languages and just be able to eavesdrop on people's conversations about physics or life. And it's really inspiring as well to be there and have people from all over the world all working together on one common purpose is really nice. There's a question asking if I'm at CERN right now. No, I'm in Amsterdam. So I work for the University of Amsterdam. I'm an assistant professor there and also with NICEF doing my research. So I spend about half my time here in Amsterdam and about half my time at CERN for collaboration reasons. So sometimes I don't remember where I am. So I have a very good calendar that tells me where I need to be. So there's a question, what is CERN's purpose? So CERN's purpose is particle physics research. So it was formed in the 50s after the Second World War, and their scientists had left Europe for many different reasons. Some of them, quite obvious and terrible. And the aim was to have a European physics lab to bring everybody back and to work on research for peaceful matters. So it's specifically written into CERN's mandate that we only do research for scientific, absolutely no military purposes. And everything that we do is open access. So we publish all of our papers completely open access. We're also sharing our data. So you can actually go to the open data website at CERN and download the data that we have. It's not all available yet, but we're releasing it in batches from the different experiments that we have on the Large Hadron Collider. And you can play around with it. So some of it is there in its raw form. Some of the experiments, so for example, Atlas, the one that I work for, we've released tools and Jupyter notebooks and guidelines to be able to play with the data interactively, as well as to play with the raw data. So you can, get stuck in and rediscover the Higgs boson or whatever else you want to look for in our data. I would actually really recommend it if you're thinking of applying to CERN, to have, if you're not already working in particle physics or something nearby with data analysis and you want to be a particle physicist at CERN, then the open data is a really great way to get some experience with that and to show that you have an understanding of some of the techniques that we use at CERN. Oh, so Daniela is asking, can I visit the underground at CERN? So until the 10th of March, we are actually open for underground visits, but it's really hard to get underground because we have very, very few tours going underground, and we can't really book them in advance. So if you want to go underground, the very best way to do it, and unfortunately you'll have to wait a while, is to wait for our CERN open days, CERN open weekend that we have. So it's usually it's a weekend relatively soon after we shut down for a long period. So it's going to be in a couple of years, but then we completely open the CERN site for a weekend. We invite people to come and you can visit lots of the different underground sites that we have at CERN. And it's one of the few opportunities for people to see the Large Hadron Collider directly, not just the experiments, which we do have tours to go underground at. So if you were specifically traveling to go underground, that would be your best chance. But if you happen to be in Geneva anyway, you happen to be passing by, then definitely come and visit CERN, because we have tours above ground every day but Sunday, and you just turn up at reception, you book yourself on a tour in a couple of hours time. It's completely free. You can go and visit the first accelerator that we built at CERN. You can often go and see the Atlas Visitor Center and see the control room where we're running the Atlas experiment. Depending on when you go visit, you might see me in there because I'm often in the control room working on the operational side of the detector when I'm at CERN and when I can be in the control room. So I don't understand this comment about my tooth. Okay. So if you want to, so I can't guarantee that you'll get to go underground. There's a very, very tiny chance, if you're lucky, that maybe you can. And if you know somebody working at CERN, that's a better way of getting underground, because people can give private visits to underground areas, but everybody's very busy. So it really depends on who's available. But if you come to Geneva, absolutely you should sign up for one of our free tours. And there's lots. You might even get to go to the Antimatter factory. That's a big one that we do, which is a great tour. You get to see the accelerator, or the decelerator rather, for the Antimatter factory, and it's where we're studying antimatter at CERN. So going on a tour is fantastic. If you're in Geneva, I absolutely recommend that you come and come visit us. Okay, let's see. I've missed some questions. And Bob's been, thank you so much for putting links in the chat. So the Open Data, Atlas Open Data website is on there, and the CERN Open Data links. And Julian's been to the Antimatter factory. Brilliant. So I'm just having a quick look at Instagram to see what questions we have here. So somebody asked, is teleportation theoretically possible? So that's really not my area of expertise. So Daniela said you're going much just to visit CERN. Excellent. So Oh, sorry, there's another question. I should move to Instagram to ask. It was on the stories. I just wanted to make sure I answered some from there as well. Yeah, if you're coming in March, then absolutely come and do one of our tours, because they're definitely, it's really cool to see, and you get to ask lots of questions live as well to your tour guide. And there's a very small chance it could be me as well, because sometimes I give tours when I'm at CERN as well. Okay, let me check then. Oh, there's a question. Have you had any mind-blowing conclusions whilst researching? That's a good question. The thing is about science is that it's not usually, people think of like, you know, the eureka moments, the jumping out of the bath, realizing that you've suddenly solved everything kind of moments. And science isn't like that. And mostly what I have is, I'm so frustrated, this is really annoying, why is it not working moments most of the time. And then I have the, that's why it's not working moments. And science is much more incremental. So the mind-blowing moments are very rare in science. I did get to attend the announcement for the Higgs boson discovery, and that wasn't quite a mind-blowing moment, but it was really powerful in the way that I got to be in the auditorium as we announced that we had discovered a brand new fundamental particle. And, you know, to hear the theorists, so Peter Higgs and Francois Englert, were there in the audience to hear them live. Yeah, so Julian says that's in 2012. So I was a PhD student at the time, and I slept outside the auditorium with friends to be able to get into that room. And that was powerful in a different way. That was the culmination of thousands of people's work over decades to search for this particle, to build the equipment, to analyze the data, to choose what data to select, to ensure that we could record it on our computers, to everything, every step of the way, designing the detectors. And then in that moment, we all came together, if not in person, but also online, to sort of celebrate this moment that we had discovered a new fundamental particle. And that was really special, and it will definitely stay with me throughout my career. It also motivates me in those moments where I was talking about when I'm like, why isn't this working? Because we have to go through those stages of frustration with our code to be able to get to the discoveries. So hopefully kind of answers your question. So is it Advait is asking, is it possible that there was an equal amount of antimatter at the moment of the Big Bang, but since antimatter is just matter moving backwards in time, the antimatter moved to a pre-Big Bang time? So this is kind of a bit of a misconception with antimatter. So when we draw matter and antimatter on, we have these diagrams that are named after Richard Feynman because he invented them, and they're quite simple looking sketches, but they're quite powerful mathematically. And one of the tricks that happens is that they draw antimatter going backwards in time. So we have time running along one of the axes, and antimatter is drawn going with an arrow going backwards in time. And it's mostly just to remind us which ones are the antimatter. They're not actually traveling backwards in time. So there's something else about the way that they turn into each other that's going on, and it's not, but also, I mean, your question was, did they go to a time before the Big Bang? And we have no idea what happened before that point in time. So we do use our collisions to look at the time just after the Big Bang, but to look at the way that we think the universe was in its very hot, dense state, to see how the particles interact with each other. But we have no idea what happened before or even at the Big Bang. So it's not possible for us to say with our data at the moment. Oh, so Oswago said, what would you suggest to get more ladies interested in STEM in general, and also do talks in general? I think, I mean, one of the things is that there are lots of women interested in science. One of the problems we have is that sometimes the environment isn't the very best. And so for me personally, one of the things I want to focus on right now is people who are already interested in science. So the undergraduates that I work with, people who are coming to science talks, I want to show them that there are women doing science. So I have lots of women colleagues who are doing fantastic work. So there are many people, for example, at CERN who are leading the science, many women that are leading the science. I mean, everybody's leading. In terms of leadership positions within the collaboration is what I mean. And for example, when the Higgs discovery happened, the spokesperson for Atlas was Fabiola Gianotti, who then went on to be CERN's first woman director general, who can't talk anymore, it's too late at night. She's still at this moment director general of CERN. And yeah, so I think it's really important to have visibility of women that are currently doing research and to show that it's already happening, if that makes sense. But yeah, also I also go and give talks in schools to try and show younger audiences about the work that I'm doing, and I talk on social media, so it's why I have this YouTube channel. Please subscribe if you're not already subscribed. And it's why I do science communication on other social media platforms, so that it just sort of spreads the message that, I mean, I want to talk about my research, but it also spreads the message. Sorry, I just saw a troll in the comments. Yeah, so I want to spread the message about my research, and I want to show that there's a woman doing science in physics, and there's lots of women doing science in physics. Yeah, sometimes, I don't know, I've gone off on a weird thread because of the, the comments that keep popping up on the screen. So, okay. So there's some comments in the chat about being afraid of the consequences of CERN running, and I just want to reassure everybody that the collisions that we're doing at CERN, these proton collisions that are happening in the center of the detectors, they are already happening in our atmosphere, and they have been happening for billions of years. So what we're doing at CERN is actually not unique. It's happening in nature all the time. There are high energy particles coming from outer space colliding into our atmosphere. And so, for example, Higgs bosons are getting created all the time, and any other particle that could be created in our collisions are getting created all the time, and then they're changing into other particles or fizzling out. What we're doing at CERN is doing it in a controlled way, where we know that we're colliding protons together, and we then surround those collision points with our detectors, and we do it trillions of times in a specific location so that we can measure the particles that are coming off from these collisions and understand what our universe is made from on on the smallest scales. Thanks for the timeout, Bob. So yeah, there's nothing to be worried about, because what we're doing is happening all the time in our atmosphere. Okay, so Hester is asking, where are you originally from, and do you like living in Amsterdam? So hopefully that answered your the last question. So originally I'm from the UK. I'm from a city called Coventry. I lived there up until when I went to university in Manchester. So I don't really have a Coventry accent anymore. My accent is kind of flattened out and mixed, because I spend a lot of time with people from all over the world. So yeah, you can tell me where you think my accent's from. Sometimes people get the UK, but then other times I get told it's a bit, yeah, mixed up. How do I like living in Amsterdam? I really like living in Amsterdam. I've been here almost half a year now. But I spend a lot of time at the university and I spend a lot of time traveling. So I still haven't been to very many museums yet. They're on my list of things to do, and I'm really looking forward to spring and just wandering around and taking photos in front of the canals, of the buildings, and just getting to know lots of little shops and yeah, more of the heart of the city. So I haven't done as much as I would like. I was in Nijmegen for a while, and then unfortunately with COVID, I got locked down, not in the Netherlands, but I really like Nijmegen as well. So I also want to do some traveling around the Netherlands and see lots of other different places around the country as well. Oh, so, and Andreas says, can we observe Higgs bosons if particles travel faster than the speed of light? So there's two questions there. The first question is, can we observe Higgs bosons? And the actual answer is we've never observed a Higgs boson directly. They change into other particles so quickly that we never measure a Higgs boson in our detector. What we're measuring is the particles that Higgs boson changes into, and then we have to reconstruct those particles from the traces that they leave in our detector, and then we collect all of the collisions that happen, and we can see that there are bumps in our data or other signs from the data that we've collected that there is a Higgs boson, or that there is a Higgs boson. We can never say that an individual event had a Higgs boson in it, because again, there are lots of different ways that particles can change into each other. But what we can say is, after collecting all of these events together, we waited until we were so confident that there is a Higgs boson creating these kind of changes in our data, that if there wasn't a Higgs boson and it was a statistical fluctuation, it would be a 1 in 3.5 million chance that just through statistical fluctuation alone, this would happen. And then we waited until the other experiment, CMS, had exactly the same confidence level, above the same confidence level as well. So we were really, really confident that the changes that we saw in the data that we were measuring was because there was a Higgs boson, and not just because the statistical fluctuations in the data were misleading us. Then you're asking about things traveling faster than the speed of light. So no particles can travel faster than the speed of light. This is one of the sort of laws of physics that we have. It's the speed of light in a vacuum. Massless particles travel at this speed, and everything else has to be traveling lower than this speed. It's just one of the laws that we have in the universe. So there was some suggestion that there might be particles traveling faster than the speed of light a few years ago with the opera experiment. The neutrinos they thought were traveling faster than the speed of light, but it turned out that the cable, the optical cable for the experiment was not connected correctly, and so there was a systematic error in their measurement. My tea is getting a bit cold now, but it's okay. It's still tea. Oh, so Sky is not the limit says, if tachyons exist, would CERN have picked up their effects in the detectors at this point if they are naturally occurring at least? So that's yeah. So you're also asking about negative mass particles. So we haven't observed anything like that. So for tachyons, we've not observed them. If they happened naturally, it would really depend how they would show up in our detector, and we're definitely looking for them. We're looking for anything in our detector that doesn't look like what we usually expect. And we're also, and Bob knows very well about this, we're also now implementing machine learning techniques as well in our data to learn also what the standard model expects to show up in our data, and then just looking for things that just look completely different. So in that case, we're not even specifically saying one theory over another, which is often what we do in particle physics. We say, okay, how about supersymmetry? How would that look in our detector? And then we plan out exactly how it would show up, and then we measure that. Bob's happy with machine learning being mentioned. And that's one way, and it's a really important way because it's a very precise method for looking for new particles in our data. But we can also use machine learning and anomaly detection methods to just say, hey, does anything look weird? Does anything look different? And that's also another great way to look for new particles, and they could be tachyons if they exist. So we're definitely looking out for them, but sadly there have been no signs so far. Two more questions. Is there implementation of AI in your research with increased AI takeover like ChatGPT? And what does a day in the life of a particle physicist involve? So the first question, yes, absolutely. So I already kind of mentioned it just now. So we do have AI in our data analysis. More specifically, we use machine learning. So for machine learning, we train different types of machine learning algorithms depending on the specific question we're asking or technique we want to use. And then we can use that to help us separate the data better, or to look for signals better in our data. So it's being used, and it's actually been used in our analysis techniques for over 25 years. I mean, I'm pretty sure, I don't know if exactly the top quark discovery, which was in 1995, used machine learning techniques. But I know that at least later on in the top quark analysis at Fermilab, they were already using machine learning techniques. So we've been using it for a very long time, and because we have such huge amounts of data, we need that kind of, we look in all these different dimensions of parameter spaces. It's getting technical now, but and when I say dimensions, I mean, like, I don't mean alternative dimensions, not like Marvel, but machine learning can help us look at the data in ways that sometimes even our brain can't perceive. But it's not AI, because it still needs the physicists to train it and to guide it and to analyze the data that's coming out. But it's very useful in our studies. ChatGPT is a language machine learning algorithm. It's mostly looking for predicting the most likely word to come next. So it's why you can ask it questions and it will give you very confident but sometimes wrong answers. Like, sometimes it does great things. If you ask it to write something, if you ask it to write about the Higgs boson in the style of Shakespeare, it can do that really, really well, because it can predict what the most likely thing a Shakespeare thing would say. But if you're asking it about facts, sometimes it will just tell you what is the most likely word to come next, and not necessarily the actual fact. So it's good to also double check what it's telling you, and it's definitely going to get better as well. And it has its uses. Obviously, it's been very powerful already. Oh, and the next question is, what does a day in the life of a particle physicist involve? So that's a really good question, because it's also very different for each particle physicist. So when I was doing my PhD, for me, because I was working on the hardware, my day involved going into a clean room, and I'd actually wear a white coat and protective shoes on, and I would take prototypes of the sensor that I was developing, and I would study it with a probe machine. So I would check that all of the connections were working properly. I might take it to CERN to study in a test beam. So then I would be on shift, putting it in a beam of muons that we have at the test beam and checking whether it performs the way that we expect it to. I then might take it to a radiation facility, which we can do at CERN or in other places, irradiate that device and see how it performs after aging it, 10 years in the LHC. And then I would analyze that data. So I'd spend a lot of time in front of my computer. And unfortunately, a lot of the day for a physicist involves meetings, lots and lots of meetings. So sitting with colleagues, discussing improvements to different analyses or plans for experiments that are happening next. We have people from all over the world, so we were using online meetings before the pandemic. So ever since I started my PhD, I was getting used to doing online meetings. So we spend a lot of time talking, but we have to, because there's a lot of very complicated things going on, so we have to keep everybody up to date. So Al is asking what an antibody is. So that's outside of my expertise. I am not a biologist. It helps us fight diseases. But for that question, I would definitely ask a biologist, unless you're talking about an antibody made out of antiparticles, in which case don't high five them. So I'm just looking at the next questions. So you said you asked a question about, so somebody said they asked a question on Instagram. I didn't update them, so I'm sorry if I missed. So if I didn't get to your questions, I can also try to, I see the question. A group involved in, did it separate them? Sorry, no, I'm just rambling. So the question is, CERN involvement in neutrinos experiments other than June. So, I mean, neutrinos are involved in our measurements in ATLAS, for example, but we can't measure them directly. So we infer that they are missing from the particles we do measure in our detector through looking for missing momentum. We also have a detector that is down the beam pipe near the LHC. So when you have the LHC collisions happening, they happen in the center of ATLAS, for example, and then they carry on down the LHC, and because of the magnets, they get bent around the LHC beam pipe. And then they put this other detector called phaser, which is down the beam pipe, not bent by the magnets, but straight down. And they want to measure, so they started by measuring neutrinos, so they measure neutrinos directly. And they're also trying to measure other types of particles that could have been created in the collision, and then they pass through and are detected down the beam pipe. So potentially types of dark matter or other non-interacting particles in the they have to be neutral because they're not bent around. So there's also phaser that did measure neutrinos directly because they put emulsion layers in the detector that then were able to measure a couple of neutrinos. But neutrinos really don't interact with anything, so it's very unlikely that they will interact with the detector. So you need trillions of them to be created in the collisions to be able to just measure a couple. So I'm just checking the questions. Are there easily measurable effects a significant distance from the accelerator? Like, could the field from it affect cloud formation above it? So often you might, there's sometimes there are conspiracy theorists that say that we are affecting the weather at CERN, and that is not true. So there are no measurable effects from the accelerator or the detectors a distance away from them. So I used to say that I'm pretty sure you could stand in the control room of the ATLAS experiment and you wouldn't be able to know if the magnet's on unless you looked at one of the screens. Maybe with very, very sensitive equipment, that's still close enough. But the strength of the magnets for the LHC are the equivalent of magnets for used in MRI machines. And there are, I don't know, millions of MRI machines around the world, maybe hundreds of thousands, and they don't affect the weather at all. So what we're doing, it's the field strengths are very high locally, but the field lines are closed. And so they're not, once you get like a couple hundred meters away from the machine, then you can't tell that it's on or measure what's happening there, and it definitely doesn't affect the clouds nearby or the weather formations. What does ALICE and ATLAS have in common? So these are two of the experiments that we have on the Large Hadron Collider. So ATLAS is the experiment that I work on. It's one of the two general purpose detectors, which means that we are just trying to measure everything that comes from the collisions and reconstruct that and understand the particles that are formed in the collisions. ALICE is similar, and it has a similar structure to ATLAS in that it has a tracking detector and other sub-detectors in it, but it is specifically designed to measure heavy ion collisions. So lead atoms that have had their electrons stripped away can also be accelerated in the Large Hadron Collider. And we collide these in the center of the detectors, and especially in ALICE. And it creates, because they're much heavier and more dense, it creates this unusual form of matter called the quark-gluon soup, or the quark-gluon plasma. And it's similar to what we believe the universe was like fractions of a second after the Big Bang, in the very, very early universe, when the quarks and the gluons weren't confined together inside of hadrons, but they were able to sort of mix and be all soupy is where the name comes from. And it's a really interesting thing to study, and that's what ALICE was specifically designed for. Thank you. So sky's not the limit says, thanks for the reasonable and straightforward answers, by the way. I really appreciate that. So mostly this was to test out the setup for this this way of doing things. So I didn't prepare loads in advance. I'm mostly just wanting to have a chat. I'm gonna probably end in maybe about 10 minutes, if not before, because I should also call it a night soon because it's getting pretty late here in Amsterdam. So the question is, are you aware of other neutrinos experiments CERN has joined, for example, June, which would be designed to observe CP violation in neutrinos and antineutrino interactions? So as far as I'm aware, no. So CERN hasn't fully joined June, as far as I'm aware, but it's working on Proto-June, which is a study of the detectors at CERN using the beamline facilities that we have at CERN. That technology will be used at June. But as far as I'm aware, I don't know of other experiments CERN might have joined. Mostly CERN does its experiments in-house, like ATLAS and the other experiments that we have. Great. Yeah, so Daniela says, thanks, I hope I get to see you at CERN. I'm not sure if I'll be around then, but I hope, if I am, then I hope I get to see you. And thank you, Jeff, for the nice comment. So I did see that there's a comment about if black holes open, what would be the percentage of surviving it? So we know that the Large Hadron Collider won't create massive black holes. This is already known before we started, because the energy level that we're colliding at is already happening in our atmosphere. So nature has been running this experiment for us for billions of years, and the Earth is still here. The reason that it was brought up and it was discussed is because people were talking about micro black holes, which possibly could have been created in our collisions and also in the collisions in our atmosphere. And if these were created, they're not massive black holes, they would fizzle out. But so far, we haven't seen any evidence of them. It would actually be quite interesting if we do. If those are created, then your chance of survivability is 100%, because we know that, again, they're not created in our atmosphere in a damaging way, so it would be fine in the LHC as well. If you happen to be in space and a black hole, massive black hole opened near you, I'm pretty sure you're never escaping it. So I don't recommend going near a massive black hole in space. So there's a question, what is the most difficult calculations you have done in your analysis? That's a great question. I don't use a whole lot of like really difficult maths. Most of my work now is computer programming and sort of logical problems. I have mathematics in there, but it's not particularly challenging. I'd have to think about that one. Mostly also I get the program to do my calculations for me now. So yeah, one of the questions is, as you finish, could you say what you're hopeful to achieve? Well, for me personally, I would love to understand what dark matter is. I have no preference on any specific theory. I have no hat in the ring for any of those, but I would just love within my career to find out what it is, even if that means one of the other experiments works it out, or B, I would love it if we could work it out at CERN, what dark matter is. That would be a huge achievement. And otherwise, just find some new stuff out about the universe. That's what I'm here for. That's why I do my job. But I can't really make any. I'm an experimental physicist, so just have to take what I'm given and try and study the data and see what's out there. Is it possible that the universe can be infinitely small? Can there exist smaller particles than the fundamental particles we're aware of? So that's a great question, because we've often thought in history, we've thought, okay, atoms are the smallest thing that could possibly exist. And then we found out about protons and neutrons and electrons, and then we found out that protons and neutrons are made up of quarks and gluons. And so I would almost say it's arrogant to think that we're completely done. And also we have all these questions that we've mentioned before about what else there could be in our universe. So it's possible, and there are lots of great theories that are proposing smaller, more fundamental particles than the fundamental particles we think are there. But we need evidence for it. So at the moment, we don't have any indication, for example, that the electron is made up of smaller things. But we're definitely looking, and as we do our analyses, that's the question we always ask. For example, is the Higgs boson fundamental, or is it made up of something even smaller? That's a question that we ask in our research. So it's a great question, but we don't know at the moment. So we're going back to the calculation question, calculating a cross-section or the efficiency of the detectors. Yeah, I mean, we do that in our analyses, but mostly I program that into my strings. Tom says strings. Maybe strings. But as an experimental physicist, I need to have something to measure. But my computer screen was saying hello to me then. It was telling me it was telling me a setting about the screen. Mostly I put the calculations in my code, because it's also a better way to do it. Then I don't have to do the calculation every time I run it. It just does the calculations for me. So thank you for joining. There's a comment there saying good night. No, that's a good point, that the cross sections are you can calculate the cross sections once, but if you want to do it, depends on the precision that you want to do it at. Okay, so I hope I haven't missed too many questions in the chat. I'm probably going to call it a night here. Thank you so much for joining. I really enjoyed answering all your questions. I'm going to continue investigating the setup and seeing how I can do this better every time. So if you do have any feedback, please let me know. And hopefully I can even do some lives from CERN next time I'm around, maybe from underground, we'll have to see. But definitely answering more questions. So if I didn't get to your question, if you're watching this video later, then please put it in the chat and I will always pop by and try to answer as many questions as I can. If you're not subscribed already, then I would really appreciate it if you could subscribe to the channel. It would be great if you could give it also a thumbs up, because that helps this video get seen by more people. And yeah, I really appreciate you hanging out with me, asking your questions, and yeah, see you in another video, or maybe even at CERN. So have a great night or day or morning, wherever you are, whenever you're watching this, and hope to catch you again soon. And thanks so much to Bob for doing the moderating. That was really helpful. Thank you very much. So yeah, take care and see you around. Bye.